Alright, so in this video I'm going to be explaining another important article about domain adaptation, which is called pseudo-label guided unsupervised domain adaptation of contextual embedding. So this paper in 2021. And still it is unsupervised domain adaptation. Contextual embedding models such as BERT can be easily fine-tuned on label samples to create a state-of-the-art model for many downstream tasks. However, the fine-tuned BERT model suffers considerably from unlabeled data when applied to a different domain. In unsupervised domain adaptation, we aim to train a model that works well on a target domain when provided with labeled source samples and unlabeled target samples. In this paper, we propose a pseudo-label guided method for unsupervised domain adaptation. Two models are fine-tuned and label source samples as pseudo-labeling models. To learn representation for the target domain, one of those models is adapted by masked language modeling from the target domain. Then those models are used to assign pseudo-labels to target samples. We train the final model with those samples. We evaluate our method, unnamed entity segmentation, and sentiment analysis. So as I said, we have two models. So we have two classifier, and for general pre-trained model, we have classifier 1. For target domain pre-trained model, we have classifier 2. And then we have unlabeled target samples here. Then we use the pseudo-labels that we have learned with the pseudo-label target samples for classifier 2 to get for classifier T. So pseudo-label guided unsupervised adaptation consists of 3 steps: jointly fine-tuning, pseudo-label generation, and final. So there are 3 steps. The first one is jointly fine-tuning. As you see, we are fine-tuning. The second one is pseudo-label generation. This is the generated pseudo-labels. And finally, final adaptation. After that, this is what we call final adaptation. So first, we initialize 2 pre-trained models with the same architecture as a general pre-trained model and a target domain pre-trained model, which leverages language modeling objective on unlabeled data from target domain. In the second step, we use those 2 fine-tuned models to make predictions for unlabeled target samples. If both models agree with the prediction and 2 prediction scores exceed the threshold, the prediction is regarded as pseudo-label. Finally, all pseudo-labels are collected to fine-tune the target domain pre-trained model and complete the adaptation. So we are jointly fine-tuning. In the first stage, we jointly fine-tune the general pre-trained model and the target domain pre-trained model on the source domain data to obtain 2 classification models, F1 and F2. These are 2 classification models. Their predictions are utilized to give pseudo-labels. We assume each sample in the source domain can be denoted as X sub I and Y sub I, and X is just a text sequence, Y is a label sequence for NES task. So for name entity segmentation, the token representation are fed into output layer at the output. For sentiment analysis, the CLS representation is fed into the output layer for classification. Inspired by the asymmetric tri-training adaptation method, we design a multi-view constraint laws to encourage model F1 and F2 to make predictions based on different viewpoints. So we add this term W1 transpose W2 to the cost function, and they are just the output layer. They are the output layer weights of model F1 and F2. So each model learns from different features. As I said, we have two models, F1 and F2, and both of them use cross-entropy laws. But we have this hyperparameter lambda we design it based on validation split because it's a good trade-off. And with the multi-view learning, the pseudo-labels can be more informative and improve model accuracy. After jointly fine-tuning, classification model F sub 1 and F sub 2 are used to generate pseudo-labels. Pseudo-labels will provide target discriminative information to the model. However, since they certainly contain false labels, we have to pick up reliable pseudo-labels. For text sequence in the unlabeled target domain, we add pseudo-annotations to the sequence and add single pseudo-label Y to the sequence in the SA task. So intuitively, if the two domains are closely related, the pseudo-labels are assigned to a large portion of target samples, while distant domains will reduce the amount of agreement. And we expect the threshold of agreement to keep the pseudo-label reliables and maintain a probable number of samples. So we use pseudo-label target samples to construct a training set of the target domain and further fine-tune the target domain pre-trained model with this training set. Since the accuracy of the pseudo-labels cannot be assured, we use a smaller learning rate and fewer training steps to fine-tune F sub 2 with pseudo-labels. So we initialize both models, F1 and F2. But of course, we initialize F1 with BERT, but F2 with TDPM. Then we train them. But here we are using that if they agree and maximum of their label is greater than threshold, then we add it to our training pseudo labels. Then we train. After that, we got everything. Then it's just a supervised learning. After that, it's just a supervised learning. So Connell is very simple data set. As you see, we have high performance when we go from source to target. The source is Connell dataset and the target is WNUT dataset. So here we have low F1 score.